Let's see.
Okay. Well, let's get started. So thank you to everyone who's called in to our webinar hosted by the Statistics and Pharmacometrics SIG, which is a joint special interest group with ISOP and ASA. So this is one of our initiatives, was to help put out more content that is relevant to both statistics and pharmacometrics. And a goal of ours was to have a quarterly webinar series. And this is going to be the first webinar in that series. So a little bit about, what is the Statistics and Pharmacometrics SIG? So if you haven't, if you're unaware of this special interest group, then welcome. So we're really excited to have you here, and we're excited for everyone who's already a member. But a little bit about the Statistics and Pharmacometrics special interest group. So this was created in 2014 as a joint initiative between the American Statistical Association and ISOP, International Society of Pharmacometrics. And the goal was to have some cross collaboration between statisticians and pharmacometricians to help both our disciplines learn and grow from each other, and help develop innovative approaches that will really be important for model-informed drug development and push it forward. Some of our goals for the SIG are to provide educational opportunities to learn about statistics and pharmacometrics. So this webinar is within that realm. So we're trying to present more content and get it out there that's relevant to both stats and pharmacometrics. We want to encourage career growth and mentoring for people new to the field, promote cross-disciplinary methodology and research and publications. Really, we just want to learn to grow from each other, as well as kind of create some best practices for both disciplines. And ideally, we like to have a common place where we can share code and share ideas. So please join our special interest group. It's free, it's really easy. We don't spam with a lot of material. We won't share your information. And we hope that this could be a helpful resource for you. So please join, and make sure that when you see the email asking you to confirm, if you don't see it, it's probably in your junk email, which basically happens every time with Gmail. So, but please join, and we hope that you enjoy this content. So with that, our two speakers today, we're really excited to have them. The first one will be Oliver Sander. He's in the early development analytics at Novartis. He holds a degree in computer science and received a PhD in computational biology from the Max Planck Institute for Informatics in Saarbrücken, working on protein structure function relationships and the molecule basis of the HIV cell entry. So since joining Novartis in 2008, he's worked in the pharmacometric modeling and simulation and biostats group, mostly on projects in autoimmune disorders, infectious diseases, and ophthalmology. So he will be giving our first talk, and then we'll have time for some questions. And afterwards, we'll have Christian will be presenting. So Christian Bartels, he's also at Novartis in the pharmacometrics modeling and simulation group. He studied molecular biology at the Biozentrum in Basel to focus then on data analytics, modeling, and simulation. After some notable contributions to proteomics, protein structure determination, peptide folding, and drug design, he specialized into pharmacometrics. Since joining in 2009, Christian works in the modeling and simulation group in Novartis, supporting compounds across the portfolio. So with that, I'd like to pass the ball to Oliver, who will be giving his talk. So, Oliver, are you able to share?
Yes, can you hear me well?
I can hear you, I just don't see anything.
Yes. So just give me a second to share the presentation. Do you see the screen? Do you see the slide?
Yes.
Okay, great. Thanks very much. So good morning, good afternoon, everyone. So welcome to this webinar. This is a joint work together with a number of colleagues from Novartis that I'm going to present here. And so the topic of this first part will be estimands and pharmacometrics. And so what estimands are, why we think they're important and relevant for pharmacometricians as well. And in particular, like why we think that they help us being more precise about what we're estimating as pharmacometricians. And in this presentation, as I'll just like briefly outline three points that I'm going to address throughout the presentation. So first of all, we do believe that precisely defining what we intend to estimate is important for pretty much anyone who is in the business of estimating something. And so, of course, this also would then apply to pharmacometricians. So it's not just for statisticians, but also for pharmacometricians that we should do as best as we can, trying to understand and precisely define what we are actually trying to estimate. And on this topic, I will specifically speak about what before how. So essentially that it's important to get clarity on what we are trying to estimate before we get into the technical details of then how we're going to estimate it. In the second bit, I'm going to argue that the so-called ICH-9 addendum on estimates is a useful framework for thinking about estimates and can also be useful for pharmacometricians to think about estimates and to clearly communicate about estimates. And I'll go through a case example. So this is a case example around a proof of concept study where doses that have been scheduled per protocol have been missed or could have been missed due to the COVID pandemic. And I'm essentially looking at this case example through this lens of estimates and what this means for estimating something using pharmacometric methods for this kind of scenario. So what is the ICH-9 addendum? So I'm sure many or if not all of you have actually heard about this, and at least some statistical colleagues speak about this. So the ICH-9 addendum is essentially a guideline that came out 2.5 years ago. And this essentially proposes a new framework to define estimates. And to like give a kind of very brief definition or kind of intuitive understanding, an estimate is essentially the target of estimation. It is what you intend to estimate. And what this really emphasizes is that one should think about and one should kind of try to clarify and specify what one wants to estimate before the technicalities of then which method to use to estimate it. One could argue that the ICH-9 addendum has really a focus somewhat on treatment effect estimates, and it's maybe also a bit more focused or kind of leaning towards confirmatory trials. However, we do believe that also for other kinds of estimates, also for other kinds of studies, so including exploratory studies, and including estimates coming from other people doing estimations, including pharmacometricians. Some of the thoughts and some of the structure and thinking in this guidance is actually helpful to think about what we are estimating. In this presentation, of course, I can't give kind of full justice to this guidance and can't give you a full introduction to this guidance. However, I will still try to cover a few of the main points in this guidance to then be able to speak about how we think that this is also relevant to pharmacometricians. In this guidance, so one of the sections, and I think this is one of the key parts, kind of explains or recommends 5 attributes one needs to specify to clearly define an estimate. And you see those 5 different attributes here on the right-hand side. So this is clearly specifying the treatments, the population, the variable of interest, then, and this is very important, the strategy to handle so-called intercurrent events that are not already covered in other attributes. And I'll go like in more depth about this one soon. And lastly, a population level summary. So that's essentially the summary level measure, how you're going to summarize the variable of interest and how you're, so for example, per treatment group or treatment arm, how you're summarizing the variable that you're interested in. This strategy to handle intercurrent events. So this is, I think, one of the key aspects of being clear about what we intend to estimate. And that's what I'm going to talk about a bit more in the following slides. So what is an intercurrent event? An intercurrent event or intercurrent events are events that are happening after the randomization in the trial and that affect either the interpretation or the existence of measurements of interest. And here on the right-hand side, you can see a few examples of intercurrent events. So for example, here the first patient throughout the study, so after randomization, kind of halfway or like a third through the study, had some tolerability issues or adverse events, and then therefore the dosage was changed in that patient. And this dose change due to tolerability issues, this is an intercurrent event that might affect the interpretation, here in this case, of the primary variable that you take at the end of the trial. For the second patient, again, the patient had some tolerability issues, but then actually, and that's the yellow cross, decided to withdraw from the study. So the patient dropped then out of the study, which means that the primary variable for that patient at the end of the study or at the primary endpoint is not available. So in this case here, the intercurrent event of some tolerability issues and like positive dose reduction does lead then later to study discontinuation and thereby affects the existence of the measurement of interest. For the third patient, that patient died during the study, and again, this means that the primary variable actually could not be assessed at the planned point in time. Again, the question: how do you account for this? How does that contribute to the interpretation of the results of the study, or how do you want to attribute for this in your analysis and in your estimate? And the fourth patient here is a patient without any intercurrent events that would affect the existence or interpretation of the primary variable. Other examples of intercurrent events could be missed doses, could be any form of dose up-down titration, could be rescue medication intake, for example, could be a switch to some other treatment option, for example, due to non-response or due to adverse events or inability to tolerate the experimental treatment. So there's a wide range of possible types of intercurrent events. Now, what does it mean to think about a strategy to handle an intercurrent event? In the ICH9 guidance, there are 5 possible strategies listed how you could deal with a certain type of intercurrent event. And so here for this presentation, I'll only focus on 2 of them, so only on two of the 5. But actually all of these 5 and possibly even more could be of interest. So in this presentation, I will focus on the first 2. The treatment policy strategy and the so-called hypothetical strategies to handle intercurrent events. The treatment policy strategy is essentially addressing the question, how does the primary variable or the primary outcome look like, regardless of whether the intercurrent event has occurred or not. So regardless of intercurrent event occurring or not. On the other hand, the hypothetical strategy is asking the scientific question, if the intercurrent event had not occurred, what would the primary variable have looked like? And as you can notice here already, so essentially these 2 different ways or strategies of dealing with intercurrent events, they really correspond to 2 different scientific questions. And this is really one of the key points of this whole addendum is clarity about the scientific question, then what it means to answer that scientific question, and only then get to the details of how one is going to estimate this. Excuse me. So what's in this for the pharmacometrician? So as I already mentioned, being clear on what we're estimating is of course relevant in my opinion for a pharmacometrician as well. And if one thinks back of like the last analysis one has done, if I were to ask you if you like what were intercurrent events that affected your outcome of interest and what strategies you use to handle these intercurrent events, it's actually intuitively not very easy if you haven't thought about this before to know actually what the estimate was that one addressed with pharmacometric analyses. And just being more clear about that upfront and then doing that with more intention, I think is an important thing to do. Secondly, this also helps having a common language with statisticians and clinicians. As I mentioned, since the introduction of this ICH9 addendum, that this quite strongly affected, for example, how studies are planned, documented, how protocols are written, and also how statisticians and clinicians discuss what the goals and the kind of targets of estimation are for studies. And of course, to be able to talk to statisticians and clinicians about this, it's useful to be also familiar with that kind of language and the framework of thinking. Also, quite importantly, this, for example, facilitates discussion about why estimates might be different. So one can, so having this estimate framework clearly in mind, one can, for example, distinguish between whether the what two different estimates are estimating differs, or if the how is different. So in essence, whether the estimate is different, or if it's two different ways of estimating the same estimate. So kind of two different questions or only two different answers to the same question. And having more clarity about that and understanding where discrepancies in results or interpretations might come from, this can be very useful for. And lastly, and again, I think this is a quite important point, pharmacometric methods might also offer ways of estimating. So the how to estimate for some estimands, so the what we try to estimate, that are hard to estimate otherwise. And in Christian's second part of this webinar, you'll also hear a bit more about this. So now coming to the case example. So here, and this is really for illustrative purposes mostly. So thinking of a proof of concept study, so an early development phase study with potentially missed doses. And this is essentially based on theoretical considerations around such a proof of concept study in an ophthalmic, so in the ophthalmic therapeutic area. And it essentially was based on kind of preparing for potential issues in such a study coming up that could arise due to the COVID pandemic. And to understand the setting, so we're like in the study, it's planned to give 3 monthly doses. So these are injections into the eye. And however, some of the doses might be missed due to somewhat unforeseen circumstances that are not directly related to the patient health or drug response. And in this case here, the COVID pandemic, where, for example, the study sites, like some study sites could close due to local restrictions. It could be difficult to get the drug substance to study sites, and therefore patients might miss doses, or patients might not be comfortable kind of going outside and traveling to the study site to get their monthly injection. So like a whole number of reasons why, due to the pandemic, patients might have missed doses that are not directly related to the kind of health status of that patient to begin with, but really kind of caused by the pandemic circumstances. On the left-hand side, you see the plan, the scheduled dosing as per protocol. So like all the patient, we're supposed to get 3 doses at month 0, month 1, month 2, and then at month 3, there would have been the primary variable for the primary readout. However, and this is what you see on the right-hand side, the actual or observed dosing could have ended up differently. And so here, for example, patient 1 and patient 2 like could have gotten doses as scheduled, as planned. However, patient 3 is missing the 3rd dose on month 2. Patient 4 is missing the 2nd and 3rd dose, and patient 5 is missing an intermediate dose. So it's missing the month 1 dose, but did take the month 0 and month 2 dose. So this kind of as understanding the setting that we're interested in here. Now, what are the treatment policy and hypothetical estimates or strategies to deal with intercurrent events that I mentioned before already? So consider this case example that I've just shown with the intercurrent event of missed doses. And it could be missed doses either somewhere intermittently, or it could be that doses were taken up to a certain point and then doses were discontinued, or treatment was discontinued then after some time point. What is the treatment policy estimate in this case? The treatment policy estimate tries to answer the question, what is the effect of assigning the treatment regardless of whether doses were actually taken as scheduled or not? On the other hand, the hypothetical estimate is, what is the effect of the treatment if it were taken according to the prescribed schedule. And as you can see, these are two different questions. So it's quite likely that you will get two different answers for these two different questions. And it might not be obvious to begin with, kind of which of these questions you actually might be asking. And therefore it's so, or might want to be asking. And therefore it's so important to kind of try to add this like a layer of preciseness in what is really the question you're trying to address. So which of these two questions that could you be interested in, or could you be interested in which scenario or which circumstances? The treatment policy estimate allows a causal effect estimate without making additional assumptions if it's from a randomized study and if there is no missing data. And this reason is actually one of the main reasons why these treatment policy estimates and somewhat related to that, these like how it was kind of formally called intent to treat estimates, like why they're so popular, that you do not need to make additional assumptions and still get a causal effect estimate. However, note that this causal effect estimate is the causal effect of assigning the treatment, not of taking the treatment. On the other hand, the hypothetical estimate could be considered as an estimate to assess the full potential of the regimen. So what if patients had taken all the doses as planned? In this example here, where the doses were missed due to the COVID pandemic, the hypothetical situation without the intercurrent event, so with no missed doses, you can argue that this is actually a quite relevant, or hopefully a relevant scenario for later future real-world use, where you say, well, if patients would not have missed those doses due to the pandemic, what would the effect have been in those patients? One can also argue that this hypothetical way of addressing intercurrent events, so this what if doses were taken, that this is more relevant in a learning type setting. So like in particular in earlier phases of drug development, maybe one can argue it's somewhat less relevant for a confirmatory type setting. So if in a, let's say, confirmatory late phase study, some patients are not taking doses, the question of what had happened if they had taken all the doses might not be enough to convince, for example, health authorities, regulators, that the drug works as you intended to work. They might focus more on a treatment policy estimate. However, in a learning type setting, such a hypothetical estimate can be extremely relevant and useful. Note that this is also very closely related to what Lou Scheiner has called method effectiveness, and so which he contrasted to use effectiveness, which again roughly corresponds to the treatment policy type approach. Now, what does such a hypothetical estimate now look like, or how would kind of one come up with such a hypothetical estimate for this case example? So again, in the protocol, so let me just quickly switch over to the pointer here. So in the protocol, the scheduled dosing was monthly for every patient, month 0, month 1, month 2. However, then, due to circumstances like the pandemic, the actual or observed dosing differed from that. And some patients missed doses either individually or towards the end of the treatment period. Then in the study, one, of course, can observe response. So here, and again, this is just an example. So it could have looked like this. So on the control arm, you see essentially like a flat treatment outcome or treatment response. Whereas on the active arm, you see a lowering, which in this case would correspond to an improvement. So you see some lowering, but then it starts coming somewhat up again. And so now what you see on the right-hand side, the observed dosing and the observed response, this is the data that you collect from the study. And based on this, one could now try to answer the question and say, well, if I'm interested in this hypothetical estimate, what would the response or what would the effect have been if patients had taken all the doses? And this is what one could now try to answer here on the left-hand side, where here, if you look at the curves, you see that the active curve, for example, stays more down and doesn't kind of start relapsing back towards control, but really kind of the difference, the treatment effect between control and active stays wide under this hypothetical scenario if patients had taken all doses as planned. how does one estimate such a hypothetical estimate? Actually, as it turns out, often kind of typical pharmacometric analyses do target such a hypothetical estimate. So if, and it's, can argue if this is kind of a standard way of doing things, but if you estimate the model taking actual dosing records into account and observed data, of course, and then use that estimated fitted model to simulate from that population model with a certain scheduled or hypothetical dosing, then what this leads to is a hypothetical estimate. It's a hypothetical estimate regarding what if patients had taken all the doses as planned. An additional benefit of using this approach is that this, of course, also does allow for extrapolation to different doses, for example, or also extrapolation to different regimens. One very important aspect here is that here in this case, the intercurrent event of missed doses was independent of patient health and independent of drug response. If this independence is not given, or you can't kind of plausibly argue for this, you have to be very careful and think about potential confounding. And this is something that Christian will speak a bit about in his part of the presentation as well. So here essentially, so we're arguing that actually what we often do is estimate a hypothetical estimate. However, it's also possible to simulate or estimate treatment policy estimates. And to do that, one could either simulate using actual dosing records together with post-hoc estimates for the observed subjects. If one is doing that, however, one needs to be aware that one then cannot use such a model or such a simulation to, for example, extrapolate to different doses or different regimens. What one could also do is implement a dosing or compliance model, where, for example, the relationship between dose and dose intake or compliance is somehow captured in the model. And then this could be used to simulate out then dosing and PK and PD and response. Again, if there are some dependencies, so for example, if unlike in the example that I've given here, the intercurrent event is not independent of patient health. So for example, if missed doses might be due to, let's say, adverse events or due to lack of efficacy, then one would need to think of building a joint model where essentially these interdependent events or outcomes are jointly modeled, and only if one has such a reliable joint model, one can then use that to simulate treatment policy estimates, for example. So again, to summarize, I hope I could convince you that precisely defining what we intend to estimate is important for everyone estimating something, including us pharmacometricians. And I hope I could explain a bit kind of what's meant by this what before how. So try to get clarity on what you really intend to estimate before getting into the technical details of how you're going to estimate it. The IC89 addendum is a useful framework for thinking about this and for doing this. And I would really recommend to everyone to have a look at this document. It's I think it's about like 15 or 20 pages, so it's not a very large document to read. And I think it's really beneficial for any pharmacometrician to just have a look at this document, even if it's just to understand some shared language with clinicians and statisticians. And I went through this case example, which I hope made the kind of abstract concept of estimates a bit more concrete and helped kind of show what this really specifically means for different types of pharmacometric analysis one might be interested in doing, and that it's really worthwhile kind of being clear upfront what type of question we're trying to answer, what kind of estimate we're intending to estimate, and then what is the right method to estimate that estimate. And so here just like two quick references. We've put together one brief paper about estimates from a pharmacometric perspective that might be useful if you're interested in more about this, and of course the IC89 addendum itself. And that concludes my part of the presentation. And I think then Luke or Tim might take over again.
Great. Yes. Thank you very much, Oliver. Nice presentation on an important topic. We have a couple of minutes for questions. If you have any questions for Oliver or for Christian later on, please click on the Q&A button and type your question in there. So we can take a couple of questions now. We'll take some more at the end as well. So just one question to start with. So this ICH E9 addendum focuses on statistical analyses. So you've talked about the pharmacometrics applications, but do pharmacometricians have to follow that specific guidance as well?
So to my knowledge, I haven't heard from examples where, for example, health authorities would expect pharmacometricians to really use that language or specify, let's say, in a pharmacometric analysis plan, like planned estimates or analyses using that kind of language. So I do think that we don't have the same kind of expectation to use it, at least as of now, compared to statisticians, which where like right now it's expected from regulators to use that kind of language and that kind of framework in clinical study protocols and analysis plans. So we don't have that obligation. But however, as we've argued here, I do think that the whole framework to think about what we're trying to estimate is useful right now for pharmacometricians as well. So I think kind of even without being forced to use it, I think we as a discipline kind of benefit from adopting and you know, starting to gain some experience with that framework and kind of start using it to gain experience in where we might want to adapt it in some sense. But also what the pitfalls, what the limits are, and yeah, in the end, kind of what this means for us. But I think in principle, the importance of being clear what scientific question precisely we're trying to answer and what we're trying to estimate, I think that is, I hope, kind of clear that while this, you know, should apply to every one of us.
Sure, thank you. So another question, which estimand is better, treatment policy or hypothetical estimand? I mean, well, the obvious answer is it depends. It's so you cannot give a kind of clear-cut answer that one is always better than the other, and it really depends on the scientific question of interest. And so let me try to jump back a few slides. So as I try to outline here, so it's like both have their own kind of pros and cons. And so really a strong advantage of the treatment policy estimate is that you do not need a lot of additional assumptions. And in particular for confirmatory or late phase studies, that is a very strong kind of appealing quality of treatment policy estimates. And on the other hand, as I argued here, I think especially from a kind of learning type, like learning kind of perspective, I do think that hypothetical estimates can be very relevant. But of course, we also do need to understand that for a confirmatory late phase study, if kind of the only evidence you're showing to a regulator is, well, if the patients would have taken all the doses as planned, then it might have worked. That like this might not be a convincing argument after confirmatory trials. But during drug development, especially in the learning phase, I think that's a highly relevant question to ask. All right.
And in particular, if it's regarding some intercurrent events that like either you hope to go away for some reason, like here in this COVID example, or if it's intercurrent events that you like might hope to have a way of addressing. So let's say if patients missed doses due to let's say some tolerability issues related to drug intake, and you could foresee a way of dealing with those tolerability issues. I don't know, either different formulation or I don't know, co-administering corticosteroids with some injection, to address hypersensitivity reactions, or like if you see a way to in the future address these intercurrent events, then asking, okay, what would have happened if those intercurrent events would not have happened, I think is a highly relevant question during drug development.
Okay, thank you. So we have time, I think, for one more question before we move on. There's some good questions coming in, but we can hold those until after Christian's talk. Just one more. How do Estimands differ from intention to treat versus a per protocol analysis? So intention to treat seems similar to treatment policy, and then per protocol seems to be similar to hypothetical Estimands. So is that the same thing with a different language, or are these talking about different concepts?
Yeah. It's so it's not the same thing. I do think that there are some kind of parallels in I don't know, the philosophy or the thinking behind these concepts. So like the like intent to treat and treatment policy, I think the kind of philosophy behind them is like there's really a kind of shared philosophy behind, where you say, well, it's only about assigning the treatment, and kind of I ignore whatever happens afterwards, and regardless of whatever happens, I only look at what has been assigned. Having said that, there are some like subtle differences, and I don't want to go into too much of that detail. There isn't. I don't know if people are interested in. We can like try to dig out some publications as well. I mean, there's some literature on this in particular, explaining, okay, what are the subtle differences. But I think for treatment policy and intent to treat, the kind of like fundamental philosophy behind is very similar. And hypothetical versus like per protocol, I think that's I think those are kind of a bit more divergent. And so as you might be aware, that there has been a lot of criticism of like completers analyses or per protocol analyses, because like protocol deviations or being a completer or not might actually select for very different populations on the active and the control arm. This essentially then means that such analyses would essentially compare treatment outcomes in two non-comparable populations. So it's like one could argue that then therefore it's not a causal effect estimate anymore. Whereas here, these hypothetical estimates, they are still under certain assumptions intending to provide a causal effect estimate.
Okay, great, thank you. So with that, let's move on to Christian's talk. So thank you very much, Oliver.
Thank you.
Christian, I'll hand it over to you. And then, as I said, we'll take some more questions at the end. So if you have questions for Oliver or Christian, please open up the Q&A and ask them in there.
I make a quick comment. This is Luke. I just want to also say thank you to Camille Vong. She's not here today, but she really spearheaded this webinar, and I spaced on mentioning her earlier, but she's an author on both of these papers, I believe, and was really, she deserves a lot of credit for making this happening, and I'm sure her contributions to this work was significant. So just want to throw out a just big thank you to her, even though she couldn't be here today.
Okay, so then I try to go into the second part, into pharmacometric modeling and simulation and causal inference, which is somehow related to the estimate framework. For us as pharmacometricians, I think almost always when we do modeling and simulation, we think in terms of causality. We want to know what happens to exposure if we change the dosing regimen. We want to know what is the effect of the changed exposure on outcome of the patients, which are clearly causal questions. This is in quite some contrast to what I see when I go into literature on causal inference, where there seems to be almost no overlap of the language and the methods used in causal inference and pharmacometrics. And what I'm going to try to show that there is actually quite some overlap, but we need to make it more explicit. And it's others who have also started to do that, so it's not the only. So in the larger context, when we do clinical research, we want to inform treatment decisions. So what change in outcome should we expect if we administer this drug? And this is clearly a causal question. And as Oliver mentioned already, in clinical research, the most important tool to answer these causal questions are the randomized experiments. However, sometimes the causal clinical question of interest cannot be answered relying on randomization alone, and we need to complement it by assumptions. That is recognized by the estimate framework, and the estimate framework defines the causal question of interest. It talks about intercurrent events that interfere with the observations and the randomization, and then proposes strategies to handle them. On the other hand, we have pharmacometrics modeling and simulation, which, as I'm going to argue, is well suited for causal inference on clinical trials and has established ways to correct for confounding, and has even a large potential if it goes into the direction of longitudinal exposure response data. What I can offer here in this presentation is first to familiarize ourselves with a few concepts of causal inference, in particular directed acyclic graphs and counterfactuals, and then, having introduced those concepts, start to discuss how modeling and simulation in general and pharmacometric modeling in particular can be used to answer the causal questions. As already mentioned a few times, randomization is what the best that we can have, as it allows to estimate causal treatment effects without additional assumptions. We can imagine like this, that if we have randomization, then the subpopulation that receives one treatment is representative of the entire study population, and we can then compare the treatment effect in the entire study population for the two treatments to each other and get a causal estimate of the causal treatment effect. Now, if we have intercurrent event, we can, for example, not observe some of the patients, or the effect is changed in some of the patients, and then we are not anymore sure that the patients that we observe, or what we observe, is representative of the entire study population, and there may be confounding, and we're not sure whether we can get a causal estimate. So here we need additional methods and vocabulary to handle these situations. And one of the tools that has been introduced over the last 20 or 30 years is counterfactual outcomes, which is a way to write down what we want to estimate. And here it's a simple example. We can say that here this Y1 is the effect of taking the drug, and the Y0 is the outcome if the drug is not taken. And if we have that in all the patients, it's simple to note down what we want to know. The causal treatment effect is simply the expectation of those two quantities, difference in the expectation. Or if you want to know the causal effect, the distribution of the causal effect, it's just the distribution of this counterfactual outcome. The problem is illustrated here on the right. If we do an experiment where patient receive only either drug, one here, or placebo 0, the D, then we do not observe the counterfactual outcome in all patients, but we observe the counterfactual outcome of receiving the drug only in the patients that got the drug, and the counterfactual outcome of placebo only in those that got placebo. And the question is then, how can we get those counterfactual outcomes that are not available? So can we, for example, estimate this counterfactual distribution in which we are interested here on the left, based on what we observed, the outcome in patients that receive active treatment, or can we do something else? So counterfactual outcomes are helpful to define what we want to estimate. The second tool I'm going to briefly introduce are directed acyclic graphs, which are useful to express assumptions on what we assume is happening and how different things are interrelated. So here it's a simplified clinical trial where there's a randomization. So patients are randomized either to active or placebo. Then they go home, and at home they are encouraged to take the drug, but they do not always take it. And this gives them the outcome. And we assume here that age affects the dosing and the outcome. And as such, age is a confounder which affects both the dependent variable and the independent variable. And that's a situation that may lead to problems, as I'm going to show in a few moments. Now, what are the strategies to get causal estimates of the treatment effects? So the one we had already is randomization, which corresponds to what Oliver discussed in the estimate framework as the treatment policy estimate. So we ask, what is the effect of assigning treatment, regardless of whether the doses are taken or not? And looking at it in the DAC, it's the same DAC as we had before, but here we marked randomization as the intervention and the outcome as in what we are interested. And what we see then here is that in this situation, age is not a confounder, as it does not affect directly the randomization. So we have no effect of age on randomization, and as such, it's not a confounder. And in this situation, we can actually estimate the causal effect of randomization on the outcome based on what we estimate. And here I used to draw this nice tool, Dagiti, which allows to draw the DAX. It allows to say what is the intervention, what is the outcome, and then also gives an assessment of whether there is confounding, and gives also test possibilities to test ways to adjust then for this confounding. Then going to the hypothetical estimate now. Here we're not anymore interested on what is the randomization doing to the outcome, but we want to know what is the dosing doing to the outcome. So what is the effect if we actually give the drug? And in this situation, age is a confounder, as it affects both the intervention and the outcome. And Dagiti tells us with the red arrows that we have this confounder, and that our observed data cannot anymore be used to give the causal treatment effect. To discuss this in more detail, I go now to an even simpler example, where we have as example, vaccination for COVID, where people get vaccinated, and we observe whether they are hospitalized or not. And age is a confounder in that older patients are more likely to get the vaccination, but they're also more likely to end up in the hospital. And what was discussed now almost 2 years ago in the news, if we do the naive thing and just estimate the efficacy of the vaccination based directly on the observed data, we get the confounding and we get the wrong result, since age affects both vaccination rate and hospitalization. However, one can correct it by doing an analysis per age group. So we can adjust by age group, and within each age group, we see that the vaccination works nicely, and the average of the age-adjusted vaccination rate is then quite good. And this approach of adjusting by age is called standardization, and it's also related to what is referred in causal inference as the G formula. Now, this G formula looks in the first, or this standardization looks on first sight quite different from what we do in modeling, simulation, and pharmacometrics. And I permit to put in one slide to explain what is pharmacometrics, since I'm not sure, since all of the audience here knows what it is. So in one slide, to try to summarize pharmacometrics modeling and simulations for those who are not used to it, we are trying to use semi-mechanistic models. We fit them to the data, and then we simulate the outcome of interest. And often, as I will come back in a moment, the models are longitudinal, so we describe the data over time. Over, we consider the exposure, concentration in the body, and the clinical outcome together. So we have dose exposure response. Often it's using differential equations to describe these relationships, and often also we use mixed effects model to describe between subjects variability. So the question is, how does this modeling and simulation, which we all think is causal, relate to methods such as standardization, which are put forward in the literature on causal inference? And a first step is to realize that the standardization, or G formula, is actually a form of modeling and simulation. It's in the books here, but also Jim Rogers, I think, who attends this seminar here, has also put together a very nice publication recently. So the standardization formula is here. So what we have done, when U is the age, D is the dosing, and Y is the outcome, we said that we need to have the outcome condition on the vaccination and the age, calculate this for each age group, and then average over the age group to get the causal distribution of the outcome for the vaccinated or unvaccinated patients. And what one can see is that this average over the age groups, we can actually substitute by an average over the patients that we observe. So instead of having here probability of the patient having a certain age, we do simply have the sum over all patients, and then it corresponds to the probability of patients having this age. So this standardization we can substitute by a sum over the patients. And as then shown on the next slide, this corresponds quite closely then to a modeling and simulation approach. So what we need to do is we establish the model based on the observed data. And then based on this model, we simulate the outcomes for each of the patients and for the different treatment arms, are vaccinated or not vaccinated, to get our sample of the simulations. And then to get the distribution of the hypothetical outcome, counterfactual outcome, or the expectation, it's sufficient to actually summarize these simulations. So we can get the probability of hospitalization if being vaccinated simply by calculating the mean here, or the protection from hospitalization by vaccination by calculating this ratio. More generally, the modeling simulation is a generic approach for causal inference. So as just said, we need to build the model based on the observed data, simulate the outcomes of interest, and then summarize the simulation results. And to account for observed confounding, we need to use DAGs, or DAGIT is convenient to identify the confounders, and that need to be adjusted for to obtain the estimate of the causal effects. We need to include the confounders into the model. In the example, we need to have age dependence on the effect of the vaccination and the outcome. And then should probably also ensure with model diagnostics that the effect of the confounder is appropriately captured by the models if we do not use only trivial models. So that's relation between modeling and simulation and standardization, which is used in causal inference. However, pharmacometrics modeling and simulation is more than just modeling and simulation, as I mentioned before. So we have the exposure response component, we have the nonlinear mixed effects modeling components, we have longitudinal aspects, and have a strong impression, and I'm going to argue in the next slide, some of these approaches that we are using pharmacometrics may actually be quite advantageous for causal inference and help to correct for confounding. There has been relatively little work done so far, and the work needs to bring together pharmacometrics, estimate framework, and causal inference. My impression is that we will see a few publications, quite a few publications actually in the next few years on some of these aspects. For example, we have dose exposure response analyses where usually we assume that all the treatment effect is mediated by the exposure, so that the dose is not directly giving a response, but only via the exposure. And in the literature on causal inference, this is called front door adjustment. And in books of causal inference, Pearl, or in his book of causal inference, Pearl complains that there are actually no good examples where this is used, but we are using it regularly. It's just that we need to better establish it and make it more clearer. Then the next two bullets are a little bit related. So we do modeling of longitudinal trials. If we go into the literature of causal inference, we find cheat computation and sequential conditional exchangeability as keywords how to handle those longitudinal trials. In our work, we do not use sequential conditional exchangeability, which is essentially autocorrelation. We would sometimes look at autocorrelation, this goes this direction, but we do usually not use this, but we use random effects to describe the longitudinal aspect and the correlation between subsequent observations. And this conditioning on random effects is something which is not often done in causal inference and literature on causal inference, but we find a few papers on it which look into latent variables in Bayesian dynamic networks. And my impression is that this conditioning or using random effects as a way to condition then on unobserved confounding has also a huge potential. And it's again something we should probably work on and make more explicit. And then finally, in the later examples that I provided, there was no randomization anymore. But when we do modeling and simulation, we usually have the randomization. We check that our models are correct for each of the randomized treatment groups. And having this randomization and checking that our model captures it corresponds to something which is in causal inference referred to instrumental variable. And our models implicitly, they have express how treatment is expected to work, which corresponds to treatment homogeneity assumptions in the literature of causal inference. So also here, there is something where probably we can, the two fields can contribute to each other, where the pharmacometrics approach goes to longitudinal trials, uses instrumental variables for longitudinal trials, which is rarely done in causal inference. So for all these points, I expect to see work being done in the next few years. So stepping out back again into the big picture. So to answer causal questions, different approaches may have to be combined. Randomization is clearly the primary tool in clinical research. It gives homogeneous groups for comparison and avoids confounding. If there is confounding, one needs to do more. Intercurrent events are an example for this confounding, something that could introduce confounding. And we do need to do more. We need to consider estimate framework. We should consider causal inference. And as I said, pharmacometrics is well positioned. We can use DAX to better represent our assumptions. Modeling and simulation is a generic approach, called essentially G computation, causal inference. And beyond modeling and simulation, pharmacometrics modeling and simulation seems to be very well placed to answer causal question. And I would encourage everyone to think about this and try to make it more explicit more often. A few acknowledgements of people who helped in addition to the co-authors on the first slide to bring this together, and then a few references that might be help to find some additional points to read. And with this, I have finished my presentation. Thank you.
Okay, thank you very much, Christian. Another nice presentation on another important topic, and tied together nicely with the Estimands concepts as well. So we have time for some questions. So please type your questions in the Zoom Q&A. I'll start with a few questions for Christian. Well, I guess these are causal inference questions, so they'll go to Christian, but Oliver can chime in as well. So to start off with, so this is from Jim Rogers. Thank you for these excellent presentations, and thank you also for the mention of our recent publication. So the question is, for those of us who already believe in the clarifying power of causal inference concepts, what do you see as the best way to promote broader awareness of the value? And do you see any opportunities for relatively quick wins to demonstrate that value?
Yeah, it's a good question. I think the best thing that has been done recently is actually the publication from Jim Rogers. So we have to find small pieces that are small examples that can be put into publications and discussed, where the two pharmacometrics and causal inference go nicely together. And probably quick wins are the front door and dose exposure response, where I think causal inference is not having good examples, and we are using it very often. That's perhaps one of the quick wins. So we have to find examples, publish.
Right. So another question on the causal inference topic. It seems like with DAGs, you need to know upfront which confounders are present. Is that correct?
That's partially correct. So the DAGs represent correlations, which is essentially connection between nodes, but they are directed. And the connections you can identify based on correlations. However, the direction, you need to have external information. So yes, the DAGs need additional information. Some aspect of the DAGs can be checked against the data. And there are also some approaches to try to infer DAGs from observed data, but you need more and you cannot say everything.
Okay, and there's another question related to that. Since causal discovery algorithms are designed to learn the structure, the DAG structures, some causal discovery algorithms are designed to learn the DAG structures from the data. In your experience in the pharmacometrics world, have you seen people use these algorithms, or are DAGs usually generated only from expert knowledge?
In pharmacometrics, I've not seen it now. The dynamic Bayesian networks for proteomics goes a little bit in this direction, which I've seen, but yeah, not in pharmacometrics.
In my experience, these kind of like DAG structure inferential algorithms, so they require more data, they require a lot of data, and usually they can kind of point to equivalence classes of DAGs. So they can kind of say, well, it might be from this class of DAGs, but not from that class of DAGs. And I think only in like rare circumstances, they can really pinpoint to one particular DAG and say, well, that's the one, versus all the others. So it's a very challenging problem to infer DAGs from data. And I've seen it in the like in the biomarker world, where people tried to find these like causal links with directions from measured biomarkers, and it's a very hard problem.
Okay, thank you. So another question on causal inference. Is my understanding correct that what you refer to as causal inference is analogous to what pharmacometricians do, for example, in a covariate analysis?
As a test overlap in that if you have external covariates that, for example, affect your exposure response, then adjusting for those external covariates is important to get causal estimates. But in general, the objective of covariate search is not causal inference. It's explaining variability. And as such, the objective is different, but both include covariates, adjust for covariates, and as such, there is some overlap.
Okay. I'm going to jump back to some of the questions on Estimands. At the learning phase, the analyses will be conducted with or without applying the Estimands framework. And many analyses will need to use the totality of evidence by leveraging data from multiple trials or sources. Will Estimands make these types of analysis difficult? And what are the benefits that one could expect the Estimands to bring?
So I do think being clear about what you're intending to estimate does make sense, no matter whether it's early phase, late phase, whether you do inference about one trial, whether you do some kind of evidence combination across different trials, preclinical and clinical, external, internal, etc. So like no matter what you're essentially doing, if you estimate something, I think it makes sense to try to be as precise as you can about what you intend to estimate. And I don't really think that it's fair to say that it makes things more complicated. I think it's hard to think about this, but I don't think of this as kind of overhead, but more just as something you have to do if you really care about what you're estimating. That you really have to go through the mental effort and trying to be as clear as you can what you try to estimate.
Okay. All right. If the dependence of intercurrent events to the estimand is not well known, what methods could be used to assess such dependence, if any?
I mean, first of all, I think at the design stage of the trial, what's most important is kind of trying to anticipate. So try to anticipate what kind of events could occur and could interfere with your either measurement or interpretation of the measurement. And so anticipate is one thing. Then the second thing I believe is you will have to in most cases, you will have to decide upfront, okay, how do you want to account for this in your estimate? And there, I think in particular for late phase trials, one might end up putting together something more conservative, where so for instance, you would so let's say if a patient takes in rescue medication, so you would account for that, interpreting that as a failure of the treatment, for example. And even if you don't fully understand how this current event is then related to the outcome, you might then conservatively assume that, well, this is an indication of failure. Of course, in early development phases, kind of in a learning phase, all that data that you do collect, you can look at that data and you might learn something that you then might use for later phase studies to maybe kind of refine either being aware of additional intercurrent events that you hadn't thought of before, or also kind of fine-tuning how you account for these events in what you're trying to estimate.
Okay, all right, thank you. So on the topic of causal inference, how many clinical trials have been done that did not use this approach that may have led to wrong levels of statistical significance? I guess what I'm asking is, have you fixed a problem that did not really exist? That did not really exist.
It depends very much on the clinical trial and the question. Usually clinical trials, they are designed to answer the question based on randomization and don't need causal inference as an additional tool to answer the main question. However, sometimes there are additional questions which are not answered by the randomization, and then causal inference becomes important.
Maybe just to give one example there. So doing kind of naive analysis where you ignore such considerations. You can, for example, think of a trial where patients get uptitrated if they don't respond well. And if you naively analyze such exposure response data, you might then have a pattern where higher exposure corresponds to worse response. But this, of course, doesn't mean that higher exposure causes worse response, but those patients not responding well did get uptitrated and therefore had high exposures. So and I think this could be an example where kind of ignoring or naively ignoring such causal considerations leads to like obviously weird or wrong conclusions. And therefore, I think it's important to have that kind of causal inference framework in mind to avoid such kind of naively misleading analyses.
Right. Okay. So on the topic of hypothetical estimands, what are some of the common assumptions that we take with hypothetical estimands in the context of drug development?
So I mean, really, the core assumption is that the estimated model that you have, that this is able to like predict, simulate, extrapolate to the hypothetical situation that you're interested in. And so like in the misdoses example, like assuming that the model is capable of predicting response in patients if they had taken all the doses as scheduled. And I mean, for this example, like the kind of standard model diagnostics that would be typically used in pharmacometrics, I think are the kind of right ways of checking if a model is likely capable of doing that task.
Right. Okay. And the next question I think is, I think you've answered this, about hypothetical estimands, using those to simulate the hypothetical estimand. How do you estimate the model parameters when you have these intercurrent events? So you're talking about the misdoses. So there's ways of dealing with that. Are there different methods for different types of intercurrent events that we could take into account?
I guess
Sorry, Christian.
As one situation Oliver mentioned is if the intercurrent event occurs at random, then there's no further adjustment essentially needed for estimating the model from the data. If it does not occur at random, then you need to find a way to adjust for the non-randomness. And one option is to, for example, adjust the exposure response on the fact of whether the intercurrent event occurs or does not occur. Might be one way to adjust for such confounding that is then introduced and be able to correctly estimate the model nonetheless. And sometimes it may not be possible to estimate the model.
Okay, right. So on back to causal inference, is it possible to incorporate a series of time points into DAGs, as in pharmacometrics modeling? I guess this is about longitudinal models.
It's possible. It's in the Hernan's book, you find those DAGs in the section on sequential exchangeability. In my slides, there was one where I tried to have something like this. These DAGs become more complex and get more difficult to discuss. Also, DAGitty fails essentially if you have several interventions, or sometimes it gives wrong results. So there's more complexity, more to do, but yes, it is possible.
Okay. And what is your opinion on designs wherein the test to placebo randomization ratio is 2:1 or higher, especially for rare diseases?
Well, I guess the quick answer is like maybe talk to your trial or project statistician about this. I mean, it's not really a kind of estimate or causal inference related question. Yeah, I mean, maybe just to like give a very brief answer. It's So in terms of overall sample size, it's not the most efficient thing, but it might have other benefits that it just, for example, gives more data on active that for various reasons might be still beneficial. So there could be good reasons to do it.
Right. Okay. Some of these counterfactual outcomes, like estimation of incomplete block experimental designs, except that you aren't designing the incompleteness a priori.
I don't know.
No, I haven't thought about that before, and no, I don't know either.
Okay. All right. Another question for the causal inference. What could be the impact of bringing closer together the scientific fields of causal inference and pharmacometrics? 1 for pharmacometrics, 2 for causal inference, and 3 for statistics.
Yeah, I think for pharmacometrics, it gives, I think, more credibility and more strength if we express our simulation results better within the framework of causal inference and also statistics. For causal inference, my impression is that pharmacometrics has actually a few techniques which address things that are not well handled so far in causal inference. So longitudinal trials, this G computation with recursive simulations is not something that has become very popular, and one reason might be it's not very easy to do, and perhaps using the random effects and the mixed effects models that we use is actually in many situations a better approach for these longitudinal trials. And also the instrumental variables with multiple drug administrations is something that is rarely done, perhaps since it's not an easy problem, but pharmacometrics has one. I think there are benefits in all directions. And for statistics, I think if we do well our jobs, then pharmacometric methods may become kind of a statistical method.
Right. Okay, isn't every study a confirmatory study with respect to prior information?
Yes, depends for whom. Yeah, no, I think if you do an experiment or a study, it confirms always something, might be just for you or for internal decision. And I think we refer to confirmatory studies if we want to prove something to the world, so confirm it to the world that it's the case.
And if you look in the ICH E9 guideline itself, it like describes what is really a confirmatory study. And I mean, just broadly speaking, it's something like a phase 3 study. And like in some circumstances, it might also be like smaller studies, like a phase 2 type studies. But in general, it's something like with the rigor of a phase 3 type study.
Right. So one more question before we wrap up. Christian, you gave a nice example with the COVID vaccine, the impact of not including the age as a covariate in the model. Is the converse also true? When you neglect to, when you include a covariate or control for a variable in your model, can you other examples of when you shouldn't do that? I guess specifically in the context of pharmacometrics models.
Yes, there are situations where you should not do that. If you have a dependent variable, also we have outcome, where something depends on the outcome and on the treatment, and you then condition on that introduce confoundings, collider, and you should not condition on it. Nice thing with Dagiti is that you can just try out and it will tell you whether the things you are going to condition on are sufficient to correct for confounding or whether they actually introduce confounding. So there you can try out the things.
Right, thank you. All right, we are about at the end of our time.